In section 9.3, we're moving on from just graphing quadratic equations. Now we're going to start solving those. So first of all, what we're talking about as a quadratic equation is taking this form, ax squared plus bx plus c. And if we want to find solutions, we're always going to set that equal to 0. And we're also going to see what that looks like in a graph. Again, we're just going to call that standard form. We've seen that now for a few sections, ax squared, bx, and c. And we're going to solve them in this section using two different methods. First of all, just by graphing. And this is mostly just to get a picture of what that's going to look like. And more often, we're going to solve these sorts of functions using what we call finding square roots. So if I want to solve this, I could solve it by graphing if I graph the related function y equals ax squared plus bx plus c. So this is the entire parabola. And if I graph that entire parabola, so this example is something like x squared minus 4. Remember, that means it moves the vertex down 4 units. I would have my parabola shape still if I was graphing the whole thing. But if I wanted to find solutions of the equation, I would be looking to the x-intercepts of that graph. So x-intercepts, again, kind of like y-intercepts, just where it crosses that x-axis. In this case, we cross the x-axis here, and that would be at positive 2. We cross it also at negative 2, so the solutions of that equation, again, notice the equation is set equal to 0. If I'm trying to find a solution, it'd have two answers, one at positive 2 and one at negative 2. And we could see different situations. In this case, we have two solutions, one positive, one negative, but I could have a few different examples. We could have no solutions, we could have one solution, I could have two solutions like that last example. And in our purposes, we're going to look at solutions like 2, negative 2, stuff that are real numbers. But it is possible to use what we call imaginary numbers to solve quadratic equations. We're just going to focus on the real solutions, and solutions are always just going to mean basically real numbers here. A couple other terms you might see here instead of solutions. I might refer to this as roots of the equation. I might call them zeros of the function. Those are basically all interchangeable. We're just trying to find out when that's going to cross the x-axis. So three different types of equations: x squared minus 1 equals 0, x squared equals 0, x squared plus 1 equals 0. These are all quadratic equations that we're trying to solve. And we're solving that, in this case, by graphing them. I'm going to say that for the most part, graphing is not the easiest way to solve it. I think you guys will find the second method is going to be easier when we use square roots. But in terms of finding out what our solution looks like on a graph, and if I was given a graph, it's pretty easy to find out where our solutions are. So I'm actually going to start with the one in the middle. If I start with x squared equals 0, remember the simplest graph is what we call our parent function. So x squared is going to be the simplest shape I can make that's a parabola. And that would just be my u shape starting from 0 at the origin, because if I plug in 0 for x, I'm also going to get 0 for y. That would be my vertex, and this would just basically be my graph. Again, that's the easiest parabola graph we can make. So if I was trying to find the solutions, again, if that's where it crosses the x-axis, it doesn't actually cross the x-axis, it touches at the origin, and just intercepting the x-axis would be enough. So we'd say that point x equals 0, that's our one solution to this equation, because that's where it's touching that x-axis, that's our x-intercept, just that one point. So reason I did that one first is because these other graphs, if I was doing something like x squared minus 1, that just takes that parent function, and from our last section, we know that minus 1 is just going to move that function down 1 unit. So just kind of have a basic sketch of where that function would go. It would go at 0, negative 1 as my vertex instead of 0, 0 at the origin. And if I was trying to find my x-intercepts, again, it looks like I have an x-intercept here and an x-intercept here. I could plug some values into my function. I think what we'd find is that those intercepts are at the values 1 and negative 1. So we could say in this case we have two solutions, kind of like that example at the top. We have an x-intercept at positive 1, x-intercept at negative 1. So by using the graph of this function, where it crosses the x-axis, those are both my solutions. Again, we can use that plus or minus symbol. So what happens if I use plus 1 instead of minus 1? If I say plus 1, again, from that previous section, that means we'd be moving our graph up 1 unit. So our new vertex would be at 0, 1 instead of 0, negative 1. But since it's still a positive x squared, I'm not going to have it go through the x-axis facing downwards, not going to be a negative function. Positive x squared is still going to be facing upwards. So if it's facing upwards, and if it starts off above the x-axis anyway, this one's not going to have a solution. And again, that could still happen. As long as it doesn't cross the x-axis, we can't have an x-intercept. So no solution would be a fine example of this. And it's actually an example of what we'd have, something we call an imaginary solution. So I said that finding square roots for the most part is going to be easier for you guys. If I give that same type of function, again, this is x squared equals 81, is another quadratic equation. If I wanted to solve that, I could just take the square root of both sides And then we basically already have our answer. It's the square root of 81, which is just 9. And again, that's plus or minus because we could use either two positives or two negatives to end up with that 81. So let's try to solve that using square roots. Again, we don't have to graph these, especially if I was trying to graph this, something like negative 75 for the intercept, trying to graph it with 3 as a number I have to keep multiplying my table would be tough. I can just try to isolate, kind of like we did at the very start of the year, isolate my variable, and we're just going to do that by using square roots. So first step is a lot like what we did previously. If I want to isolate my variable, let's add 75 to both sides. So if I get 3x squared equals 75, that would be a first step. Still want to isolate, so hopefully you guys know what's next. Got to get rid of that 3 in front. Opposite of multiplying by 3 is dividing by 3. So if I divide 75 by 3, I would get 25 as my next step. And we're pretty close. All we have to do again is by using our square root. If it's x squared is equal to 25, I can take a square root of both sides. That square root is going to cancel out my x squared. And the square root of 25 is just going to be 5. And one thing we want to remember is that, that could be 2 positive 5s or 2 negative 5s multiplied to get 25. So again, that was just taking that last step at the end is really our only new step. We knew how to do everything else from before. So trying this other example, add 36 to both sides because we want to isolate for our variable. M squared is going to be equal to 36. And now is just where I got to get rid of that squared power. So that's where I'm taking my square root of both sides. Now I just have m by itself. And now we just got to remember that the square root of 36 is 6 and also that it could be plus or minus 6. Again, we have two solutions. If I was to graph that in terms of my function, it would look a lot like that first graph. We'd have a parabola that touches the touches the x-axis twice. Again, try those other examples. I'm just going to reveal our solutions for both. That first one, same thing, just subtract 15 from both sides, divide by 3 to get rid of the coefficient. The one case you come up with here, if I find that I try to take the square root of a negative, we should actually have no solution. We can't take the square root of a negative number. Doesn't matter if we have the plus or minus outside. If I have a negative inside, that's going to be not possible for an answer. So C should have been no solution. And using similar steps on the last one, isolate for a variable first. So take away 16 on both sides, divide both sides by 4. This time, if I take the square root of 0, that's just going to be 0 without a plus or minus because 0 is just 0 by itself anyway. And that's our example where we have one solution. Again, refer to this example from before. 0 would just be a single solution on your graph. So finding square roots is usually going to be the fastest method. Isolate for your variable first. Once I've isolated for my variable, take a square root. I can't do it with a negative, but if I get a square root of 0 or a square root of a positive, I should be able to get a solution. So in a real world scenario, this is our next problem, we might want to consider that the negative square root would not work. So this is what we call just choosing a reasonable solution. Even if it's a solution to our equation, it might not work in the real sense. So I drew a picture of this problem, what it's talking about. It's talking about drawing a shark-filled tank as a rectangular prism. So I drew that tank over here. It says that the height is 8 feet. The width we don't know yet. We're just going to call that W. And in the question also describes the length as just twice as long as the width. So that's just 2W. It also says the volume of the entire tank is 1,200 cubic feet. So one formula you'd have to need to know to solve this question in the first place is how to find volume. And I've given that to start with. That's length times width times height. And we have expressions for all three. The length, we don't know it, but we know it's twice the width. The width we're given as just W. That's what we're going to have to find. It's asking for the width to the nearest tenth. And then for the height, we're just given that as an 8. And in this case, we know the volume as well. We know we started with 1,200 cubic feet. So that's 1,200 equal to that right-hand side. And this is just demonstrating, again, another example of what we're going to end up with as a quadratic equation. If I multiply out, I think I get 16W squared on this right side. That was just, again, by doing W times W to get W squared, 2 times 8 to get 16. And now, just like those previous questions, what I've got to do is try to isolate from my variable and see if I can do that by using square roots. So to start with, I got to get rid of that 16, divide out that coefficient. So I think I get, what is that, 750? Nope, 75, I think, is W squared. Kind of doing this off to the side. So 75 is W squared. And kind of like other examples from before, if I have that squared power, I've got to solve this by taking a square root of both sides. So if I do take a square root, I get, I think, about 8.7. And again, that would be a plus or minus. So if we're saying that the width could be about 8.7 with a plus or minus, We know that the negative answer can't work. So far our answer is a positive or a negative, but since we can't use a negative width, we know it's got to be about 8.7 feet, and that can't be using that negative answer. So that's why we say use a reasonable solution. Even if your square root tells you that it should be plus or minus, we know a width can't be negative in real life, so we just use the positive length of the width. And this is also another example of why a graph wouldn't be best here. First of all, it's a tough function to graph. I don't really want to graph anything with this kind of an intercept like 75. But also, if I was trying to find that solution 8.7 from a graph as an x-intercept, I know it's not going to lie exactly at 8, it's not going to be exactly at 9. If it's between the two, I can estimate it, but I won't precisely be able to understand what that answer is. So again, I think best method, probably just stick to your square roots, isolate for a variable first, finish by square rooting, calculator is always fine, and that's how you can solve our quadratic equations.